Good morning, good afternoon, good evening, everyone from wherever you're joining us, and welcome to the first webinar in the Neurophysiology 2023 series. Today's webinar is titled Integrative Physiological Responses to Exercise Heat Stress, Sex as a Biological Variable, featuring Dr. Nisha Charkoudian, Division Chief of the Thermal and Mountain Medicine Division at the U.S. Army Research Institute of Environmental Medicine. Today, she will summarize the integrative physiology of responses to exercise heat stress and discuss the implications for athletes and the military. Before we get started, we would just like to acknowledge our partners for the series: the American Physiological Society, the Society for Neuroscience, the Federation of European Neuroscience Societies, the American Autonomic Society, and Scientist.com. We'd also like to say thank you to all of our series sponsors for helping to make everything possible. Now, without further delay, I am excited to welcome Nisha to join me. Hi, Nisha.
Hi.
Please begin your presentation.
Okay, thank you so much, Sydney, and I'd like to thank all the organizers for inviting me for this to kick off this exciting series. As Sydney mentioned, the title of my talk today is Integrative Physiological Responses to Exercise Heat Stress, Sex as a Biological Variable. This is my standard disclaimer for the U.S. Department of Defense, and I have no COIs or financial relationships to declare. I thought I'd start out with one slide just talking about Eucerium and who we are, because a lot of people in the physiology and neuroscience communities maybe are less familiar with military-based physiological research. We are the U.S. Army Research Institute of Environmental Medicine, and we're located in Natick, Massachusetts. We're not a university, but we have 3 research divisions that are similar to university scientific academia scientific divisions. The division that I'm the chief of is called the Thermal and Mountain Medicine Division. There's also the Military Nutrition Division and the Military Performance Division. These are, as I mentioned, analogous to academic departments, but I think of them as like a hybrid because really we have scientists and that are both civilian and military, and our military colleagues also have, of course, military duties to perform. So we do research that's relevant to the military, and we also do some basic science as well. So I thought I'd start off today by talking about this concept of the female warfighter. My colleagues Holly McClung and Gabe Giersch and I recently published this paper in Medicine, Science, and Sports and Exercise, and it covers a lot of different areas that I won't be talking about today regarding women as military personnel. But we know that females in the military as a percentage are increasing year over year. And unfortunately, as many of you in the audience probably know, the research that's done for athletes or for military personnel regarding exercise physiology has primarily been done in men, if you look over the past several decades. Now, that's changing recently, and I would say over the past 20 years or so, that's increased quite a bit, the research in women. But what I wanted to focus in on for today's presentation is this idea of environmental stress and exercise and how that impacts women in particular, or why and how we should consider sex as a biological variable when we're studying these questions. As a brief historical context, I like to include a few bullets about where we've come from, kind of. In 1928, for example, women were deemed too fragile for Olympic endurance events, and their participation was banned, so they were not allowed to participate. If you look back to find what the rationale was for that ruling, it seems to have been based on anecdotal observations and lack of rigorous controls, leading to an assumption of impaired thermoregulation in women. In 1972 was actually the first time women were allowed to participate legally in the Boston Marathon. But prior to that, there were some women who tried to participate by hiding that they were women. And then if you look at the research from the 1980s and 1990s, you'll see continuing concerns regarding women's ability to thermoregulate effectively during endurance events. However, if we look at all the more quantitative research between the 1990s and the present day, you'll see that there's no evidence that women are at greater risk of heat illness when all the usual precautions are taken for both sexes. So if we think about sex differences in body temperature and blood pressure regulation, so if we think about the autonomic nervous system controlling body temperature and blood pressure and how these differences might interact in men and women, one of the things, I think in part since I work for the military and in part just because these are the kinds of questions people have, I often receive questions about sex differences that are asked in terms of whether something is better or worse. So for example, are women better at regulating their blood pressure when they're young and premenopausal? In general, we know that women have lower blood pressure and less risk of hypertension prior to menopause compared to men. So is this better? Well, it is in some circumstances, but on the other hand, women tend to be at greater risk for so-called hypotensive disorders such as orthostatic hypotension and postural tachycardia syndrome. If we think about body temperature regulation, and I'll talk a little bit more about this in a few minutes, people ask, are women worse at controlling body temperature, like I mentioned in the previous slide? Is there something impaired about women's ability to control body temperature? Well, probably not, first of all. And there are a few examples that I'll share with you today where very high exercise intensities and heat stress are associated with lower maximal sweating rates in women, but these do not appear to put women at an increased risk of heat illness. And in fact, may be more efficient if there's a higher sweating rate in some circumstances, such as humid environments where the sweat can't evaporate. That might actually just lead to more dehydration and isn't very efficient in terms of body temperature regulation. So again, it really depends on the circumstance. And that's why I think these questions about better or worse, advantage or disadvantage between sexes isn't particularly helpful in terms of framing the questions, because often whether something's better or worse depends on a lot of specifics about the circumstances as to whether a specific tendency is better or worse. And even more importantly, in my opinion, is that there's a lot of inter-individual variability across both sexes. So if you say women might sweat less, or some women might sweat less than some men, well, some women are very heavy sweaters and some men are not very heavy sweaters. There's a lot of inter-individual variability in blood pressure and cardiovascular regulation, blood flow regulation, and sweating regulation that is much greater than some of these smaller differences that are sometimes observed between men and women on average. If we just go through an overview of the physiology of thermoregulation in humans, we know that humans are exposed to a wide range of thermal stimuli, both internal, such as exercise, and external from the environment. And we are remarkably capable of maintaining core body temperature within a few tenths of a degree of 37 degrees, despite a large range of thermal perturbations. And that can be, again, from going out in a range of extreme environments to exercising or changing body position and muscular activity. So our thermoregulatory abilities are accomplished by a combination of heat dissipation responses during increases in body temperature and heat conservation or heat generation during decreases in body temperature. So today I'm going to focus primarily on heat dissipation responses relevant to exercise performance in the heat. So we know that when body temperature increases in humans, the major methods of heat dissipation are cutaneous vasodilation and sweating. Cutaneous vasodilation increases the amount of blood flow to the skin for convective heat transfer from the core to the periphery. And sweating, and more specifically the evaporation of sweat, cools the skin, and so therefore the sweating response works with the skin blood flow response to cool the body. And as I mentioned already, when sweat can't evaporate, it's harder to maintain body temperature, and this is why humid environments are so much less comfortable than dry environments in general. So we can think of the integrative control of body temperature as a negative feedback system. This is a schematic from a monograph that I published with Zach Schlater a few years ago. And if you think of the integrative control of body temperature, you can see that it's primarily the efferent, the effectors for the thermoregulatory responses are primarily sympathetic control of cutaneous vasodilation and sweating. And the central integration of how body temperature is sensed occurs at the preoptic area of the anterior hypothalamus, as well as at some spinal areas. And as you see from the figure, these areas receive input from peripheral and central thermoreceptors regarding the state of the body's temperature in terms of surface temperature, such as skin temperature and core temperature. And those when those pieces of information are integrated, they result in the appropriate thermoeffector activation, such as I mentioned, cutaneous vasodilation and sweating. Now, behavior is also listed here at the top of the figure, and that's a really important area that sometimes is the only area we can modify in terms of being able to regulate our body temperature. So if we're in let's say, a very hot and humid environment, and our cutaneous vasodilation and sweating are doing all they can to regulate our body temperature, it still might not be sufficient depending on what's happening. So we may need to use that behavioral thermoregulation to change the clothing that we're wearing, or to move to a cooler environment, or step into the shade, or things like that. So behavioral thermoregulation refers to the things that we do consciously to help control our body temperature. Now, if we think about the influences of female reproductive hormones on the thermoregulatory mechanisms, you can see the central nervous system integration shown here in the top middle of the figure. And you can see that estrogens in general tend to decrease the central set point for thermoregulation, whereas progestins seem to have the opposite effect. Now, the effect of estrogens is to promote sweating and promote vasodilation. And the influence of progestins is a little bit less well understood. But if we think of some of the estrogenic effects that have been shown to promote sweating and vasodilation, this may lead to an advantage for women in terms of heat dissipation under certain circumstances. And I wanted to include a classic study from our institute. Luann Stevenson and Margaret Kolka were two investigators in the 80s and 90s at USARIUM who did a lot of the pioneering work on skin blood flow, sweating, and thermoregulatory responses in women. And they looked at responses. In this slide, you'll see forearm blood flow, which was used as an index of skin blood flow during exercise, and exercise time is shown here on the x-axis. One of the things that we sometimes hear about the menstrual cycle is that during the luteal phase of the menstrual cycle, core body temperature is increased, which is true. It's increased slightly, usually about 0.5 degree, because of the effect of progesterone to be thermogenic and increase our body temperature. But an interesting thing that Kolka and Stevenson showed in this study was that there was a different effect in the prolonged or steady state time period of this exercise. And on the right-hand side here, you'll see forearm blood flow as a function of esophageal temperature, which was an index of core temperature. So you can see that certainly esophageal temperature starts out a little bit higher here in the black symbols, which is the luteal phase, but and the white symbols shown here are the early follicular phase, which is low estrogen and progesterone. But when they move to the luteal phase, to the steady state portion of the exercise, you can see that the steady state level of skin blood flow, shown here as forearm blood flow, was higher in the luteal phase. And the investigators concluded that this could be an effect of estrogen to promote vasodilation, in the luteal phase. So if we look at another way of looking at exercise is to look at exercise and core temperature responses and sweating as functions of how much heat is being generated by the body. So in Glenn Kenny's laboratory several years ago, they conducted some studies looking at various levels of controlled heat production. So you can see here there was a level at rest, 200 watts per meter squared, 250 watts per meter squared, and 300 watts per meter squared. At these different levels, you can see that that sweating increased, and they were studying men and women. So sweating increased in both men and women. But the evaporative heat loss was similar between men and women at most of the levels of heat stress, shown as this evaporative requirement, or E required, in the figure. At the highest level of heat stress, shown on the right-hand side, there was a significantly greater evaporative heat loss, or sweating heat loss, in men. Now, one thing I like to note with this figure is that this does indicate or suggest higher maximal sweating rates in men, which has been suggested by others as well. But this 350 watts per meter squared E required is a very high level of heat stress, and that is unlikely to be encountered in most daily situations. So again, when people refer to something like this to suggest an increased risk for women, I don't think that qualifies as something that would contribute to increased risk for women in the heat. This slide is from the same study from Kenny's laboratory, and you can see here that they measured sweating rate on the chest at rest and at these 3 levels of exercise. At the highest level of heat stress, there was significantly greater chest sweating rate in men compared to women. I have that backwards on the slide. Sorry about that. Skin vascular conductance, or blood flow, was not different at any level of exercise or heat stress between men and women. So what about body size? Sometimes that's another question that I get asked relatively often in terms of thinking about men and women, that women are smaller and maybe have less muscle mass, or what are some things about body size that might affect some of these questions? Well, we know that heat is generated during exercise by contracting skeletal muscle and other metabolically active tissue, which are linked to body mass. So if you have more body mass, you likely have more skeletal muscle, more metabolically active tissue. However, heat is dissipated when we think about sweating, skin blood flow. The dissipation of heat occurs based on body surface area. So since women tend to be smaller, they therefore have a higher surface area to mass ratio. Any item or animal or a human that is smaller has a higher surface area to mass ratio compared to a larger item or animal or human. So in many but not all environments, a higher surface area to mass ratio is an advantage for heat dissipation. So the exceptions to these are environments where sweat can't evaporate or environmental temperature is very high. There's a category of environments called, or situations called, uncompensable environments. So definitely if you have a high surface area to mass ratio and you are absorbing heat from the environment, you wouldn't be at an advantage in that circumstance. But in a lot of environments, a higher surface area to mass ratio is an advantage for heat dissipation. And another question is, well, what about quantitative risk of exertional heat stroke? So this was a study that we recently conducted. We recently evaluated risk of exertional heat stroke in 4,465 active duty US soldiers from 2016 to 2021. This was conducted using a retrospective matched case control analysis using a database that exists at USARIUM called the Soldier Performance Health and Readiness Database, or SPHERE. And we collaborated with our epidemiology colleague, Dr. Katie Taylor, and she was able to do various calculations of risk, and each exertional heat stroke case was matched with 5 controls based on calendar time, unit ID, and something called MOS, which is military occupational specialty, which means their job category. So basically they were doing the same thing at the same time in the same place. So this is one of the plots from that paper. You can see the citation on the bottom. And the most important thing in terms of this talk is that there was no difference in exertional heat stroke risk between men and women. So there have been some studies that have shown increased incidence, or there's various ways of looking at the data. But when we quantitatively evaluated the risk based on the analysis that I just mentioned, we found no difference in EHS risk between men and women. We found an interesting thing too that was surprising to us at first, that the younger soldiers in this study had a higher risk of exertional heat stroke, which is in contrast to basically all the physiology literature showing, primarily from like Larry Kenny's group and others, showing that the ability to thermoregulate as we age goes down. However, we need to put this finding in context, which is that people who are in the Army, this is a relatively young cohort, so they were around 18 to 40 years old. So, and within that age group, the younger soldiers were more likely to be doing activities or tasks that were putting them at higher risk for exertional heat stroke. So, whereas the older soldiers or the officers were folks that would be less likely to be doing those high risk activities. So we think that in this case, the age effect is the opposite of what we expected, what we would expect physiologically, but in this case was related to behavioral aspects. And I wanted to mention too, we have a paper currently in review at the American Journal of Physiology, looking at doing a follow-up analysis from the same SPHERE database, looking at surface area to mass ratio and probability of exertional heat stroke. And this again was the same population from the SPHERE database. So again, about 4,500 individuals. And we found that lower surface area to mass ratio, again, larger individuals, was associated with higher risk of exertional heat stroke. And as I mentioned earlier, when I was commenting on compensable and uncompensable environments, this finding would be consistent with primarily compensable environments during training, although we didn't look at that specifically. So I wanted to remind everyone, since I'm an autonomic physiologist at heart, that the regulation of body temperature and the regulation of blood pressure are tightly linked to each other. If we think of the sympathetic nervous system as doing a lot to regulate blood flow and blood pressure in the body, those things are related to both blood pressure regulation as well as body temperature regulation. So if we think of basically controlling vasodilation and vasoconstriction throughout the body, you can see that in terms of blood pressure regulation here on the left hand of the slide, a lot of vasodilation might lead to hypotension or low blood pressure, whereas a lot of vasoconstriction might lead to hypertension or high blood pressure. And in terms of body temperature regulation, the vasodilation would be more associated with heat dissipation, whereas vasoconstriction, especially in the skin, would be more associated with heat conservation. So talking a little bit more about blood pressure regulation, I wanted to include, again, another classic figure. This is from the textbook of Shepard and Van Houte from 1979 and shows the integrative control of blood pressure via the arterial baroreflex. So you can see here that afferent information from the arterial baroreceptors is integrated in the brain and results in efferent control mechanisms that regulate blood pressure and that minimize or buffer any changes in blood pressure that occur. So as I used to talk about with my graduate students, we know that mean arterial pressure is a product of stroke volume, heart rate, and total peripheral resistance. And if we look at this figure, we can see that the baroreflex is able to control all of those things. So certainly via sympathetic control of cardiac contractility, the baroreflex controls stroke volume. Via effects on the sinoatrial and atrioventricular nodes, it controls heart rate, and certainly via effects on the arterioles or peripheral resistance vessels, it controls total peripheral resistance. And the reason that I wanted to talk a little bit about blood pressure and its interaction with body temperature regulation is that when we stand for prolonged periods of time, especially when it's hot out, it gets much worse. We get decreases in stroke volume because of this peripheral pooling in dependent blood vessels. And this is, again, another classic figure from Rowell's textbook from 1993. And when we have body heating or dehydration, both of which occur very commonly with endurance exercise in the heat, there's a shift in blood volume to the cutaneous circulation and or a decrease in total blood volume, resulting in basically an exacerbation of this effect. So when we see body heating at rest or during exercise, we know that skin blood flow increases and central blood volume decreases. Therefore, there's a relative decrease in venous return and stroke volume for the amount of cardiac output that's required in a given circumstance. These changes contribute to decreased orthostatic tolerance with heat and or dehydration. So this is related to or contributes to the reasons why when you are out in the heat, you're much more likely to feel, whether you're a man or woman, you're much more likely to feel lightheaded or dizzy or even actually faint because of this decreased orthostatic tolerance. And as part of the mechanisms to counter the decreased orthostatic tolerance is that there's an increase in sympathetic vasoconstrictor nerve activity that occurs in response to both heat stress and dehydration. So when you get this acute sympathoexcitation, it likely helps to maintain blood pressure in the face of all these other problems that are contributing to decreasing blood pressure and causing, again, this potential orthostatic intolerance. However, it turns out that even with those increases in sympathetic nerve activity, control of arterial blood pressure during whole body heating is still potentially impaired. And this is a study from Craig Crandall's lab from the early 2000s showing infusion of phenylephrine. So they did systemic infusions of phenylephrine, which is an alpha-1 agonist, so it should cause vasoconstriction. And they looked at the change in blood pressure during this dose-response infusion in either normothermic conditions or during heat stress. And what you can see pretty clearly here is that there's a decrease in the blood pressure response to the infusion at any given dose of phenylephrine during heat stress. So this suggests that a given vasoconstrictor stimulus, at least this adrenergic stimulus, was less effective at increasing blood pressure during whole body heat stress. And then in a similar study, the same group did a tilt test. They did a tilt test during heat stress, which is actually really hard to do for the volunteers because it's really easy to feel lightheaded on a tilt table when you're hot. And what you can see here is that during heat stress, shown in the red line here, the this is a survival curve, and you can see that the percentage of subjects remaining is shown on the y-axis. Of course, they didn't die; they just weren't able to continue the heat stress. But that percentage of subjects remaining starts to fall off at about minute 5 here. Whereas if they did perform skin cooling, just cool the surface of the skin, you can see that percentage of subjects remaining stayed up at 100% right up until the 10 minutes of tilt. So this suggests that skin cooling helps orthostatic tolerance by increasing, and potentially by increasing, cutaneous vasoconstriction and total peripheral resistance. So if we go back to this figure about the influences of female reproductive hormones on thermoregulation, and we think about this influence of estrogen to promote vasodilation, maybe this influence of estradiol to promote vasodilation might augment the influences of heating to decrease total peripheral resistance in women or in people with estradiol. So what does that mean? Well, if we go back to a normothermic condition, this is a paper that Emma Hart and I published back in 2011. And you can see that this is a norepinephrine dose response curve. If you look at the left-hand side, you can see the delta informed vascular conductance. So this shows vasoconstriction in women in the black symbols and men in the white symbols. In the control condition shown here on the left, you can see that women showed almost no or very little vasoconstriction in response to increasing doses of norepinephrine. When we gave beta blockade, that was reversed. So basically the women in the beta blockade condition had progressive vasoconstriction in response to progressive doses of norepinephrine. So in normothermic conditions, estradiol seems to offset noradrenergic vasoconstriction by augmenting beta-adrenergic vasodilation. So if we think about this in terms of our overlapping mechanisms slide, what if we add heat stress? Well, if we add heat stress and we cause kind of a shift in the balance towards vasodilation, in terms of blood pressure regulation, we're probably shifting the balance towards hypotension or low blood pressure. Whereas in terms of body temperature regulation, we're trying to shift the balance towards heat dissipation. So what does this mean if you have estradiol on board and that's promoting your your vasodilation even further? Well, this is a figure from a different schematic figure from a different review paper, and showing blood pressure regulation and temperature regulation on the same figure. And again, it's kind of the same theme that I've been saying, where estradiol tends to promote vasodilation in terms of both thermoregulatory mechanisms and in terms of blood pressure regulation mechanisms. So what does this mean for orthostatic tolerance then in women during heat stress? So if we have a circumstance where we have either athletes or military or others who are trying to conduct activities during heat stress, during the activity itself, it might not be as much of a problem because of the muscle pump action on blood flow and venous return, which I'm not really talking as much about today. But when the activity has to stop at a given point, and when that happens, there may be more venous pooling or more decreases in venous return, contributing to problems with orthostatic tolerance. And in fact, it has been shown that orthostatic tolerance during heat stress appears to be lower in women. So this is orthostatic tolerance measured this was measured at the University of Oregon in John Halliwell and Chris Minson's group. And you can see they studied women in 3 different phases of the menstrual cycle: in early follicular, preovulatory, where estrogen is elevated and progesterone is low, and mid-luteal, where both estrogen and progesterone are elevated. And they also studied men at 2 different time points, just at 2 different random time points. And what you can see here is that there was lower orthostatic tolerance in women during the passive heat stress across all 3 cycle phases. It was not, in fact, different as a function of cycle phase, but just as a reminder, there is more estradiol present in women in any cycle phase than there is in men, even when the estradiol is relatively low in the women. And if we look at some of the other figures from that paper, we can see that cardiac output and stroke volume appeared to be what was contributing to these differences between men and women during the tilt intervention. So the major difference so the men are shown here in these triangle symbols, and the women in the 3 different phases are kind of all grouped together here. So the major differences appeared to be in cardiac output and stroke volume, which were lower in the women. So if we put everything together as a summary, I haven't talked that much about menopause today, but premenopausal women in terms of blood pressure regulation tend to have lower sympathetic nerve activity and higher beta adrenergic mediated vasodilation. In terms of temperature regulation, there aren't many differences between the sexes in premenopausal women, but we do know that estradiol can tend to promote heat dissipation via sweating and cutaneous vasodilation. What I haven't talked as much about today, but I'm happy to address in the questions if I can, is that after the menopausal transition, sympathetic nerve activity goes up quite a bit, as does risk for hypertension. Beta adrenergic vasodilation goes down. This is another kind of piece of evidence for the idea that estradiol is contributing to this beta adrenergic mechanism. And again, after the menopause, there are impairments in thermoregulation that are associated with aging in both men and women, but the differences between the sexes are minimal. If we think about a continuum of factors to consider when we're thinking about these, I definitely haven't talked about everything today, but if we look all the way from on the left side of the figure here, where some basic mechanisms are listed, to the right side where applications for clinicians and physically active individuals are listed, we can see that there are a lot of different areas in which a lot of work is still needed, ranging from very basic or molecular to very applied. So to summarize for today, we know that female reproductive hormones have important non-reproductive effects on autonomic regulation of blood pressure and body temperature. Estradiol promotes vasodilation and heat dissipation and can offset vasoconstrictor effects of noradrenergic stimulation. The influence of estradiol to promote vasodilation often results in lower blood pressure and/or blood pressure responses in women. And this can result in lower orthostatic tolerance in women, particularly during heat stress. There's a lot left to be done, as I've kind of just suggested. Some potential differences between men and women in terms of combined thermal and blood pressure stimuli remain to be specifically quantified. For example, there's been an interest in recent years in passive heat therapy to treat various things, to induce heat acclimation or to treat high blood pressure. There's really not a lot known, as far as I know, about how the results of that training may be different between men and women. So I'll stop there and I'll be happy to answer any questions.
Thank you so much, Nisha, for the wonderful presentation. If a person has postural tachycardia syndrome or POTS, does that mean that they shouldn't go out in the heat?
No, I would say it means that they should maybe pay a little extra attention to whether they're hydrated or not. They want to make sure they stay hydrated. They'd be a little more likely to probably have some symptoms or feel lightheaded in the heat, but that definitely doesn't mean that they shouldn't go out in the heat. It just means they need to pay a little more attention to make sure they don't get overheated.
Okay, perfect. Thank you. Our next question, sorry. Could you provide your perspective on how heat monitoring is being advanced in terms of remote wearables, such as smartwatches?
Good question. So I have several opinions about that. One is it is really important that we, for various for military circumstances, for athletes and others, it's really important that we do monitoring, that we improve our technology for monitoring. I think in some cases it's being done well. At our institute, we have a program in that area. In some cases it's being done wrong, which I think is really a problem. So I would say we need to be really careful as physiologists when we're evaluating potential wearable technology to make sure that it's measuring what it says it's measuring, and there's some proof of that validation. So yeah, I do think it's important, and I think that we just need to make sure we're doing it right, and it's not that easy to do correctly.
Okay, yeah, that makes sense. Thank you. Okay, the next one here. Thanks you for a great talk, of course. Oh, it shifted on me. Where did it go? There. Great talk. How did you define exertional heat stroke in the EPI studies that are currently under review?
Oh, right. So thanks for that question. The studies, so the SPHERE database uses the ICD-10 codes for clinical definition, it uses the medical records, and to identify someone who had an exertional heat stroke would be identified by their medical records from the hospital. Since we're going through the military medical records, there are some limitations to that because there's some things that are missed. Sometimes we think that exertional heat stroke may be diagnosed incorrectly or not diagnosed when it is there. So there's definitely some limitations to doing it that way. But we're excited to get the data that we did, the amount of data that we were able to get in the context of trying to do that analysis. But we recognize that that's a limitation.
Okay, thank you. Our next question asks, since heat increases circulating arginine vasopressin, is there a sex-specific vasopressin response to heat?
You know what? I don't know the answer to that. That's a great question. I don't know if there is and if that's been looked at. So I would have to look into that and get back to you. I meant to mention, I hope folks noticed my email address is on my slides. So please feel free to reach out. If you didn't want to ask a question in this forum, or you had additional follow-up questions, feel free to reach out via email. I'm very happy to answer email questions on email, but I don't know the answer about the vasopressin response. I don't actually. I'm thinking there is not a difference, but I'm not sure. I just thought of a paper that came out recently, but I'm not 100% sure on that.
Yeah, definitely another avenue to explore then.
Yes, that's what I'm saying. There's so much work to be done.
Yeah, that's great. Okay, the next one is kind of long. So William said, great talk. The slide showing slightly greater risk of ortho intolerance in women being related to less stroke volume increase in women. I assume this is related to less venous return in women in heat stress, which is related possibly to less blood volume. So does that mean it is even more important for women than men to pay attention to hydration when exposed to heat stress? Any sex differences known there?
Great question. Great job reading it, Sid, because it was really long. No, I do understand the question though. So it's kind of related to this body size question, which is that since women are smaller, they have less blood volume, and on average would have smaller cardiac output and smaller stroke volume anyway. I don't know that I would say that it's more important for women to pay attention to their hydration. I think it's equally important for everybody to pay attention to their hydration. I think I see what the person who asked the question, I see what they're getting at, but I would not want to say that it's more important for women. I think it's equally important. And another thing that I didn't mention during my talk, but is actually kind of an interesting finding and needs to be followed up on, is that there's some evidence that women, in terms of endurance athletic events, women are strategically better at kind of planning out their hydration or planning out their pacing to kind of maintain their body temperature and their hydration at better levels during endurance race performance, long endurance race performance, so like ultra marathons. So yes, I definitely agree that it's important, but I don't think it's more important in women because they have smaller blood volume. I hope that answered the question.
Yeah, no, that was interesting. And the side point makes sense too. Probably has something just to do in general with women having to we have such changing hormones and stuff monthly that you have to pay attention to that stuff. So yeah, I think athletes like that have definitely focused more on hydration and all those other factors. Okay. Are you aware if sauna exposure can help vasomotor symptoms of menopause, such as hot flashes?
I'm not aware if some kind of like passive heat exposure, acclimation, repeated passive heat exposure, I think is what they're asking. I don't know. I would guess that it does not help, but I don't actually know, just because a hot flash or a hot flush can be induced by heat exposure. So I'm guessing over time. I'm not sure if that would improve or not. I don't know the answer to that.
Okay. Thank you. Vasopressin, ADH, plays an important role in vascular tone during volume loss, shock, etc. Any role for it here in addition to adrenergic regulation. Did you monitor VP levels in your study?
So I'm not sure which study they're referring to, but I have looked at, let's see, in my studies, the studies I've done kind of over my career, I have looked at vasopressin, but not as a sex difference, not in terms of like differences between men and women. I agree it is a very important contributor to vascular tone. If we think about just in terms of volume regulation, if we think about vasopressin and other volume regulating hormones, there's some work from the early 2000s from Nina Stackenfeld's lab, where she showed some differences over the course of with changing hormone levels, but not so much that it would be like giant differences between men and women in terms of volume regulation. So the short answer to that question is I don't know. And the longer answer is we didn't measure it in terms of the some of the studies that I presented from our lab.
Okay, thank you for expanding. Our next question from Dr. Gupta. Thanks you again for your work. Is there a correlation between heat stroke and circulatory shock? Could you add some information on the process to counteract it?
Yes, absolutely. So let's see. There is septic shock. I mean, it's not like a version of septic shock, if that's what he's asking. We do have very specific protocols that our institute has contributed to over the years to either prevent or minimize the sequelae associated with exertional heat stroke. When someone collapses from exertional heat stroke in the field, for example, during military training, it's a medical emergency, so they are immediately evacuated to the hospital. There are things that we do, including the gold standard thing to do is really to dunk someone in a tank of ice water if you can. Now, if you can imagine some of the military bases where we have training, or some of the places overseas where people are deployed to, there's not a bunch of like ice tanks sitting around for people to do that. If we did, that would be the best way to do it. But a lot of times that isn't available. So we have other approaches. There's something called iced sheeting, where there's various ways of putting a bunch of ice let's say in a tub, like a Gatorade tank, and then dunking sheets into it, just making the sheets really cold, and then covering the person with that. That also requires ice. So depending on if people have access to ice or not, there are some commercially available products that can cool people down in the field without access to ice. Those tend to be more expensive. They work to a point, but again, it has to do with what resources you have access to. And in some places in the military bases at like Fort Moore, which was formerly Fort Benning, we work very closely with them. In some places like Fort Moore, they have their ambulances are prepared to deal with this as a medical emergency. So they'll do things like intravenous chilled saline on the way to the hospital. So there's various ways that we're working on kind of trying to mitigate the negative preventing people from having heat stroke in the first place, but definitely trying to mitigate the negative consequences if they do collapse from heat stroke. One thing that's interesting in that context is that we have, and I think this is true for athletes and the military, when you have a very motivated population, the motivation itself can be a risk factor. This is something my colleague, Lieutenant Colonel Dave DeGroot, who's at Fort Moore, is really interested in, is working on currently, is motivation itself can be almost a negative in this sense, because they might push themselves beyond their physiological signals that they really need to stop, and actually push themselves to the point of collapse. So we definitely want motivated athletes and soldiers, and at the same time, we need to kind of help educate people to strike that balance where they're not really putting themselves at risk, because you can die. People die from heat stroke every year, and it's awful, and it's really in the sense that it's always awful when someone dies, but it's very preventable. And so so we work a lot. Again, my colleague Colonel DeGroot does a lot of work in this area to try to educate as well as do research on preventing negative consequences associated with heat stroke. That was a long answer, sorry.
That's completely fine. That was great. Yeah, I'm sure. I mean, I feel like athletes and military personnel are probably the most motivated people who would be the ones to push themselves further than maybe your average person. So Yeah, that study sounds really interesting. Hopefully he gets some good results with that. John asks if there's been much research on the male/female differences in adaptation to exercise and heat, and are there adaptation limitations?
Right, great question. So there's been a little. So I think if I'm understanding the question right, it has to do with are men and women different in terms of how they acclimate to the heat? And the answer is maybe. There's been a few studies that have been done, and it looks like different mechanisms. The time course of each mechanism kind of responds differently depending on in these smaller groups of men and women. And again, it's been very few studies. First of all, heat acclimation studies are hard to do. And secondly, there just hasn't been enough work in this area. There's one ongoing study. I'll do a shout out to my colleague, Dr. Gabe Giersch at USARIUM, and she's actually in the middle of looking at some of those questions right now. There have been some studies showing that women's sweating response responds faster, whereas other responses such as core temperature changes respond more quickly in young men. But again, these are from relatively small studies, and I give them a lot of credit because those studies are hard to do, but I think a lot more work is left to be done in this area.
Fantastic, thank you. Hopefully they're on watching too.
Exactly.
Maria's question is, have you looked at pregnant women in the study as well? I'm not sure which specific one. If yes, are there any differences in how the pregnant body responds to heat stress versus the non-pregnant body?
Right. Great question. And I think the short answer is no, that really hasn't been done very well. We know that there are of course, huge changes that occur physiologically when a person becomes pregnant. There are a lot of changes in body temperature, blood volume, all the things that we've been talking about that would affect these responses. With human research, there are limitations, and we have to be with any kind of research. We want to be very careful with safety, and so in my experience, we've been hesitant to include people who are pregnant or who could become pregnant in our studies because of kind of safety and ethical issues. So I'd say a lot of that is still unknown. I think I've talked to some colleagues who are interested in looking at some of the thermal variables with pregnancy, and I think there are ways you could do it safely, but I don't think a lot of that is still unknown to date.
Okay, yeah, that makes a lot of sense. Paul asks, from your perspective, what animal models and experiments could be valuable in understanding sex differences in heat stress?
Oh, excellent question. So, well, as of right now, the only ones I'm familiar with are rodent models, so rat and mice models. I'll give another shout out to my colleague, Orlando Laitano in Florida. He's done a lot of work with, and in fact, he's starting a new set of studies with sex differences in basically mice running in the heat. And there's been some work done on that. Actually, incidentally, it seems to imply so far that women are better at it, or the female mice are better at the tolerating the heat compared to the male mice. But I know some of Orlando students are watching this, so thanks for joining, guys. So I think rodent models have been established. There's limitations with any animal model, but again, with an animal model, you can be a little more invasive compared to with humans. Obviously, we've looked at some Lisa Leon, who is my predecessor in this position at USARIUM, is now retired. She established a mouse model of exertional heat stroke, and she's contributed a lot to our understanding of organ damage. So there's specific damages to organs and tissues that occur when someone has an actual heat stroke. So that's been studied a lot in rodent models. Mice thermoregulate a little bit differently from humans. So they have this reflex kind of hypothermia after they become hypothermic after they have their heat stroke, and that helps them to recover. But so there's not really any perfect model, but I would say the rodent models that exist right now, and there's some work out about them, those are probably very promising in terms of our next steps in understanding mechanistically some of these differences.
Fabulous. Thank you so much for that information. Okay, Sean asks if you have any thoughts into the changes in beta adrenergic regulation. Is there a change in neural activation, or are the changes possibly on the smooth muscle side?
Yeah, great question. I think they're probably on the smooth muscle side. So, well, it kind of depends what you're asking. But if you think about just basic kind of blood pressure regulation, women tend to sometimes have lower sympathetic vasoconstrictor nerve activity at rest. Not always. Some studies have shown lower sympathetic nerve activity. Some studies don't. The beta adrenergic mechanism, as far as I know, is pretty consistent among studies. And so it seems like it's, either similar or lower amount of norepinephrine that's interacting with more beta adrenergic receptors on the postsynaptic side. That's my understanding of that currently. But again, that's one of those things that I may be missing something, and I'm happy to discuss.
Okay, great. Let's see. David's question, thanks you again for this great presentation. During heat stress, would you say that there is a conflict between vasodilation and vasoconstriction due to the sympathetic reaction?
Absolutely. Yes. So there is, and in fact, one of my PhD advisors was, I don't know if, I don't think he's attending this, but he might be. His name is John Johnson. He's also currently retired, but I did my PhD with him in San Antonio, and he wrote a paper during his postdoc that was called competition between vasoconstrictor and vasodilator reflexes in people, or something like that. And so yeah, so that's something I've always been fascinated by. Definitely, there's in the circumstance of heat stress and exercise, there are definitely competing stimuli in terms of blood pressure regulation. We don't want if we can't dilate every blood vessel in our body, because we'll definitely pass out if that happens. But then, we want to have increased blood flow for skeletal muscle function, and we want to have increased blood flow for skin heat dissipation. So, there's definitely competing signals going on, and I think it's the balance of those signals that ends up to be the result of whether or not we, as humans, get orthostatic intolerance or not, or just fine to kind of keep going.
Okay, thank you so much. Our next question asks if you can speculate on changes in autonomic control that might occur in young girls before and after starting their cycle.
Oh, great question. I don't really know the answer to that. So again, studying children is something that I haven't done much of, but it has its own specific set of ethical and safety concerns associated with it. I believe that sympathetic nerve activity increases, in very young people up through puberty, and I know that there are some folks that have looked at disorders such as POTS, orthostatic tachycardia, and related things occur often in adolescent girls. So there's some research that has been done in them, but I think the normal, as far as I understand it, the normal course of events is that sympathetic activity and blood pressure kind of slowly increase from childhood and then through puberty and related developmental events.
Okay, great response. Thank you. We have a few more minutes. I think we can squeeze one, maybe two more questions in. Everybody, please continue to submit your questions. We are going to pass them on to Nisha, so she should be able to answer the rest of the questions we don't have time to get to. This is a really great Q&A session, so let's continue a little longer. Have you, yes, have you looked at differences in heat stress between females of different racial/ethnic backgrounds, given potential differences in vascular function?
Right. Great question. No, I have not. And that is really something that is lacking, I think, in the literature. There's been a little bit of work. There was one study, but not very mechanistically. There was one study kind of more at a population level that came out of our institute in terms of heat stroke several years ago. In terms of women, I don't think much has been done. There's some work, I believe there's some work being done in Texas, maybe Matt Brothers' group, where they're trying to look at some vascular function aspects in I believe it's African American versus white women, and then versus men. But I'm not remembering the details on that enough to really comment specifically. I think those are really important areas for future work. And by the way, I just want to say thank you for all these questions. I really didn't expect to get this much discussion. This is excellent. Thank you.
Yeah, this is fantastic. And we have tons too that, yeah, of course we won't have time, unfortunately, to get to, but yeah, let's squeeze in the last couple. I'm going to ask this one first. The heat illness literature and international classification of diseases classifies heat syncope and heat exhaustion as distinct illnesses. Can you suggest differences in their etiology, pathophysiology, signs, symptoms, treatment?
Right. So I would say there's some overlap. With the ICD codes, they're trying to kind of simplify physiology that's pretty complicated and overlapping. And I think that happens when you have to treat something. You have to just figure out the best way to treat it. And so the clinical perspective on some of these things versus the kind of basic science or biomedical science perspective is sometimes a little bit different, complementary, but just not the same. I think you could have heat exhaustion and pass out and therefore have heat syncope, but heat exhaustion. So I view heat illnesses on a continuum. So heat exhaustion is the least serious. If you have heat exhaustion, you might feel really sick. You might go to the hospital. You might collapse. You might faint. But you're probably fine. So probably within the first 24 hours, you might still feel a little sick, but you're basically fine. You can go home. The most serious of the heat illnesses is heat stroke. As I mentioned before, it's a medical emergency. You have to go to the hospital. You'll likely have long-term consequences, et cetera. It's relatively rare, thank goodness, but it still exists. So in terms of the question, heat exhaustion versus heat syncope, I think there's some overlap between those two. I think but I do recognize that they're identified as two separate things.
Okay, fantastic. Thanks. I would like to squeeze this last question in. It's kind of just an opinion thought. What goes through your mind when you see tennis players at the US Open exerting themselves in 100+ degree heat?
So, yeah, I didn't really, I should have probably, but I didn't really talk about climate change today. It's something I think about a lot. A lot of my colleagues think about it a lot. We're getting in situations where it's more and more common to see competitive athletes, military, industrial workers working in these circumstances that used to happen, but used to be relatively uncommon, and now they're just becoming more and more common. And so, I think when I see something like that, it's concerning. I mean, obviously the more that happens, the more people are going to be at risk. And I think I hope a lot of the athletes and folks like that are working with physicians and trainers who know how to help them to mitigate some of the negative consequences of that heat. But there's a lot of people that aren't. So if we think about, like, we hear about people in third world countries who are doing like sugarcane cutting, for example, is a big public health problem. And there's folks that are developing different diseases associated with basically not taking care of themselves and being because they can't, and being exposed to these really high heat stress levels. So yeah, it's a really serious problem. I haven't really touched on that aspect as much today. So for the athletes, I think they're probably okay. I hope they are, but they're still putting themselves at risk. And I would be more concerned about the people who don't have all the resources that the athletes have, who have to put themselves at risk because they need a job. And and that really might, and that seems kind of a downer note to end this on, but I think those are some really serious things as a scientific community that we need to start thinking about some more.
Yeah, absolutely. No, I like that you pointed that out. And yeah, I don't think it's a downer. It's the reality. So, well, Nisha, that is going to be the last question. We did go like a couple minutes over, but we were just having such a great time. I want to thank you so much for your time and expertise today. It was such a pleasure to have you with us, and I hope that you had fun.
Thank you. It was so much fun. I really enjoyed it, and look forward to hearing from any folks who might want to talk with me some more.
Yes, that's great. All right. Thank you.
Thank you.
In closing, we hope you enjoyed this Inside Scientific webinar, and I hope that you all enjoy the rest of your day.